ahead and start here. Last time, I spent some time trying to explain the difference between independent samples versus dependent samples, which I'm doing today. And it turns out that you need to use different statistical methods for these two situations if you're trying to find means. Now, by the way, independent samples, this was section 3. If you do a problem from section 3, it's going to look a heck of a lot like section 2, what we did on the board. A heck of a lot like it. So even those of you that didn't get to it, this is a pretty good example to show you.
So just instead of putting in proportions,
you'd be putting in means. And what's the other big difference if you're putting in means? T instead of Z. Yeah, we don't like using the p-value. If you want to compute the p-value, you need to use your technology. I don't have a real nice way of doing it. Maybe after break I could show you on the calculator what you can do with that. Okay, so maybe we could do that. Yeah, you don't have to. You can use the back of the book. I showed you how to do that. Okay. I guess the other thing you need to know about T is we need to know DF. What does that stand for? Degrees of freedom. So we talked about that last time. Okay. So today we're going to talk about dependent samples. And when I say that, or when the book says that, they're kind of lying a little bit. They are going to show you dependent samples, but they're going to show you a very specific type of dependent sample. Because remember, dependent samples, when I write this, what I'm saying is the two samples are related. Jessie had a nice example last time. She said, look, you do a sample now, and then you use the exact same people and do the sample next week. And those will be dependent, right? Because it was the same people involved. So what we're really doing in this section, when we talk about this dependent samples, we are actually doing what are called matched pairs in the two samples. Yeah, what was that chapter problem? The freshman 15, right? Did you guys read that problem? The problem says, hey, remember that, how many have heard that saying before? The old freshman 15. You're going to gain 15 pounds your freshman year of college, right? For various reasons. And it's been here in the book? Or in here? Yeah, in this class. So what do? You do the study, and you test people now. Then you test them when? At the end of the freshman year, and then, see what happened to their weights, right? So we're going to come back to that today, actually, because that's a very nice example of matched pairs. Okay? We need some notation. So D here, you're going to see a lot. D stands for a difference, right? So say if my weight went up 20 pounds, D equals 20 for me. If my weight went up 5 pounds, D equals 5. What if my weight went down 2 pounds? You could do that. D is negative 2, right? Could happen. I would suggest not writing all this, just looking at it, because it's in the book, and seeing if it would make sense to you. If you saw that symbol, how would you try to read that? Mean of the differences. And that's what it is. And notice, it's also the mean of the differences for the population. And why did they highlight that? Because what do you think my next symbol is going to be? Yeah, what do you think the symbol is going to be? X bar D is correct, I think. Oh, they used D bar. They could have used X bar D. Our book used D bar. I don't care. honesty, to remember all this stuff is really tough. To me, that's not the important thing. That's why we use these cards. We'll have all this notation around. But you want to be able to read it when you're doing your homework. It says so this is interesting. If you take all the differences, D, add them up and divide by N, that'll be equal to the mean of the X minus Y values. Okay, so that's true. Hey, SD, guess what that stands for? Of the differences, right? Standard deviation. So we're studying differences where you're matching up the data. So by the way, you're not going to have N1 and N2, right? It's going to be true that N1 equals N2 when you have matched pairs. Does that make sense to people? It's the only way it can happen. You're using the same group. Sigma D, I guess that would be the standard deviation of the differences for the population data. And again, here, N, I'm just going to use N, not N1 or N2. But I guess, will I even need sigma D? I doubt I'll need it. But yes, that would be a nice notation for the population. Okay, a list of requirements. Every time we do statistics, we have requirements. Here they are. Yeah. We want the sample data to be dependent. The samples are simple random samples. That should almost go without saying. Either N is bigger than 30, or we know we have approximately normal distributions. Here's our hypothesis test statistic. How's that one look? Oh, don't worry too much about it. What's that? 4? Nah, honestly, it's all... Huh. See, the last ones you had, do you know what you were really dividing by? Really, the standard deviation. It's just that they actually told you what it was with all the P's and Q's and everything. Here, I guess I'm going to have to either compute these or know these. D bar are the differences. Oh, wait, what's this? This is the sample mean of the differences, and this is the population mean. And here's, well, standard deviation. And, yeah, that's a good question. We'll see. We'll see in a moment. And now, square root of n. Remember that old? We've done that before too. Divide by the square root of n, right? That was what the t distribution was. And degrees of freedom are still important. Okay. They say to use n minus 1. That's the same also. Kristen? Yes. Yeah. Right. So you're going to see that. Well, like if let's say we're doing our weights, right? We all have a weight now, and we all have a weight at the end of freshman year. If there's 15 of us, n is 15. It's not 30. No, a pair. Yeah, a pair is 2 data values. So you'd need 30 people. You would need 30 people because every person's going to have. Let's say before and after. Right. For this to work. Or if you already knew that the weights were normally distributed somehow, for some reason, some other reason, then it'll also work. Okay? And maybe weights are on a bell curve. We know that heights are on a bell curve. I saw that in the book. Remember that? They did the... It didn't say anything about that, did it? No. Go ahead. Yeah. Yeah, it's degrees of freedom. We're going to use n minus 1. Okay. P-values and critical values. You know how to do that, right? I guess we're happier with critical values when we have the t distribution. Use table A3 in the back, right? Confidence intervals. So I guess here's another formula. We know what confidence intervals look like, right? If you're trying to find a confidence interval for the what? For the mean of the differences, then it's going to be between the sample mean plus E and the sample mean minus E. So what you need is the formula for E. But actually, that looks a lot like what you've had before, right? T alpha over 2, SD over square root of n. Okay. Here's an example. Hey, this is the one in the book. It's the chapter problem. So, in Appendix B of your book, we have the weights of college students in September and April. But then it says, wait a minute, that's too big. You'll never get through the calculation in one class if you try to do this. So, let's use Table 9.1 from your book. I have it on the next slide here. Kaboom. Here I have 5 students. Now, is that really enough? That's all right. Let's pretend that we know that they're normally distributed. And they're from a simple random sample. See, actually, in this study, this was a volunteer study. So we're going to have problems there, too. I mean, who's going to volunteer their weights? Maybe that's going to put some bias in the study, right? Only at Rutgers. I mean, there's a lot of problems here, aren't there? But it says we'll proceed as if it's a simple random sample and deal with that in the interpretation. Okay. StatDisk displays a histogram that is approximately normal. I guess what they did, you know all that data in the back of your book, you could put it in StatDisk? I guess they plotted it, and they said, oh, it looks normal. Okay. And there's other ways you could test normality. But let it go. Let's say the requirements are satisfied. Hey, and look what they're doing. They have on the chart, they show the April weights, they show the September weights, and then they compute the differences, right? -1, -1, 4, -2, and 1. So you know what I'm going to compute right now? I'm going to compute D bar. Well, I'll add these up. There's -4 plus 4 is 0 plus 1, 1, and divide by 5. All right, so D bar is going to be 0.2. Is that okay? How'd I get 1? I added these. I saw that these 3 added up to -4, and I divided by 5 values. Is that okay? So there's D bar. Wow. The book goes through the steps. Let me go through them quickly. Weight gained is April weight minus September weight. Yeah, we know that. Okay. The claim is this. Mu D equals 0. Okay, I want to slow down a second because I think they skipped something. When I have an equality claim, I think of that as what? H naught, right? So I'm guessing that H1 said something else. Maybe I have to look in the book again. Go back to the actual study. Use the sample data to test the claim that for the population of students, the mean change is equal to 0. No, it says to test that it's equal to 0. All right.
Would your H1 then, do you have to infer then that it would be greater than? So trying to say that they gain.
Watch how the book does this. This is interesting. Step 2. When the claim, the original claim is that mu D equals 0, they use this. If the original claim is not true, if it's false, then mu D does not equal 0, right? So mu D does not equal 0, that's my H1. So H0 is the original claim. I don't know. To me, this is a little bit of gibberish. It's not as important here as it is, say, in that problem over there on the board. But that's okay. We have alpha as 0.05. We're going to use student t distribution. We're happy. Let's see. Hey, there's my d bar. I was right. Why do you think we put mu d equals 0? Oh, that's what h naught was, right? It said mu d equals 0. Right? That's kind of what we were testing.
So if it said 5, then that would be 5.
I guess so, but it's not going to happen. I'm just telling you. This is what we've been testing on homework problems. A lot of times you get a 0 here, and so far every time. All right, let's see. SD. Oh, there it was 0 also, right? And so it was 0, yeah. Yeah. Because that's the thing you end up testing in our problems. Yeah, it could. Then you could change things, yeah. Then you're getting a little more complicated than what we're going to do. Okay? Now let me see. T equals, and we have a big mess. I guess I know everything. Huh? Oh, how do we know SD? They told us. It says SD is 2.4. I wonder how I know that. Does it say in the original problem? Well, actually, look, yeah. Right here, guys, if we have this data, can we compute SD? What would you do? Put -1, -1, 4, -2, and 1 in your list and compute the stats. I mean, this one I did very quickly. How would I do this? Well, you'd have to subtract from 0.2. And I mean, I'm not going to make you do all that. I'm going to say, hey, put that in a list and see what your standard deviation is from your one variable stats. What?
What do you push to find out all those stats?
Oh, let me show you. All right, I'll show you. Good question. Let me do it. Hit the stat button. Edit. You don't want to write this down. You want to try it probably if you have a oh, you have the wrong one. Okay. But watch, I'm going to go on top of list 1 and press enter, and I'm going to clear this out. Okay, and now I'm ready to start typing. -1, -1, 4, -2, 1, and now I'll quit. I got them all in there.
What did you just do?
Oh, to get out of here? Second quit. Right. Now, how do I get that stuff? Well, when you hit the stat button, remember you can edit lists. That's what I did originally. But what else can you do from the stat button? Calculate. I can calculate one variable stats of list 1. I'll hit second 1 to get list 1 up there. Yeah. Hey, look, x bar is 0.2, just like we calculated. And there's SX, 2.38. If you round, you're going to get 2.4. Oops, too far. SD is 2.4. Ah! Get attacked by my software. Is that okay, Shelley? Okay. Scott? So the question is, yeah, what do you put in the list? It's the differences. Matter of fact, one way you could do this problem, you could put all of the one stats in list 1, put all the next stats in list 2, and then make a new list of differences, list 3. Subtract them. That'd be a fast way to do this. Yeah, you'd say list 3 equals list 1 minus list 2. That's right. And then compute the one variable stats. Yeah, that's a nice way to do this. Okay, so let's see. After you compute the test statistic, t equals 0.186, right? It says go to the back of the book, look at the table. DF is n minus 1. What was n? N was 5. We had 5 data points. So we're going to look in the degrees of freedom. I guess DF for us is 4. Why do I want area in 2 tails? Well, that's what you're going to use because it's going to be T alpha over 2. Okay. So 0.05. That was alpha. And they say the critical values are T is plus or minus 2.776. Okay? So picture-wise, I have a distribution, and I am 2.776 away from the mean. So here's 1, 2, almost 3. Back of the book. And you're looking at 4. Found it? Cool. So my my critical value here is T equals 2.776 and T equals negative 2.776. These are the critical values. So here's the critical regions going out from there. Okay. So yeah, now I have to get my actual T value, right? Because what was our significance level? 0.05. Let's compare it to T of, well, 0.05 with 2 tails, right? Yeah, they say this is the significance level, alpha. So what would T of 2 tails be? Oh, that's what this is. Yeah, that's what this is. I'm sorry. Yeah, that's what this is. Okay, so I guess what I need to do is I need to put this test statistic on the region. Well, actually, we do that on the next page. They have a better picture than I do. They're going to put 0.186 on the picture. It's going to be like right there. So let's see. Yeah, here's my test statistic. Right? Here's your critical regions. There's my test statistic. Are we going to reject or fail to reject? Fail to reject. So if we fail to reject the null hypothesis, what does that mean? Yeah, we can't say anything, right? We conclude there's not sufficient evidence to reject the claim that the mean is 0. See, when we have these 5 data, maybe the mean is 0 based on our data. We don't have enough evidence. Now, you could try the study again with all the data, and maybe you'd see a change. I don't know. But based on our little sample, we can't say anything. All this says, hey guys, there's bias. Let's be careful. We have lots of problems with our study that we noted when we were talking about the requirements. That's what this is saying. Let's not read that anymore. Okay, now the p-value method, you could do that with technology. I could show you guys that after break, I guess, if you want. I don't really want to waste too much time on that. And then, yeah, confidence interval, we can talk about that. Let me stop for now.